Hello, everyone. Welcome back to Resenha Cosmica podcast. We're here today with Prajwa,
Hi, everybody.
and we're very grateful and excited to have Professor Valerio Marra, who's an assistant professor studying cosmology in the University of Espírito Santo. He specializes in testing cosmological theories and gravitational lensing. So, welcome, Valerio.
Hi, everybody. Thank you, William. Thank you, John.
So I suppose most of you have been watching the launch of Euclid today, and I think we'll start with just some basic questions. So Valerio, could you maybe tell us a little bit about the basics of the Euclid telescope, the properties there, and some of the data that it will be collecting?
Yeah. So Euclid is quite a special instrument because historically he actually was born as a fusion, the merging of two other experiments, a spectroscopic one and a photometric one. And I was young at the time, so I heard this story from Professor Luca Mendola 2 times. So I think one was called Dune, that was the spectroscopic one, and the other one, I don't remember. I think anyway, they thought that it was a very good idea to have a combined probe that at the same time would do spectroscopic measurements and photometric ones. So what is the difference between the two? So the photometric measurement or imaging is like taking a picture with your mobile phone. So you take use a fancier camera, let's say. You need a camera with a very high resolution and especially a very controlled noise, electronic noise, because you want to be sure of the fluxes of how many photons you measure. And then use many fancy filters. So when you take a picture with your mobile phone, you just have 3 filters. So the standard Bayer pattern, if you guys know, it is green, red, green again, and then blue. And so you have these 3 channels. And a curiosity is that the green channel is better than the other ones, has twice the amount of pixels. So you want to do monochromatic pictures, you should start with your green channels. Yeah, and that's usually a good trick. But when we do photometry in astronomy, we use specific filters, which are similar to red, blue, and green, but they are much more precise. They select specifically features in the spectrum that we're interested in because of emission lines in galaxy, etc. And also the number of filters can vary a lot. It can go from the standard 4 filters to 6 filters or even more. For example, the case of the JPass collaboration, we are using 60 filters, 60, a lot of filters. But Euclid will use basically standard number of filters. And these again are chosen in order to select the specific properties of emission line, absorption line that then will help to characterize the what we call the spectral energy distribution of a given object. And from that to understand, for example, the redshift, the type of object, and all that. Because when you observe the night sky, the first thing that you need to do is to classify what you see. Right? The difference between amateur astronomy and professional astronomy, in my opinion, because amateur astronomers can do really incredible things, but they are more concerned, and their aim is to have pretty pictures. So they observe things that you can really observe well. On the contrary, professional astronomers, they want to observe faint stuff, at the limit of the reach of the telescope. So the picture will be really ugly. They are bad picture, at the limit of noise, with a very small signal to noise ratio. And exactly. So when you're working at the limit, a star and a galaxy and a quasar and other objects are very similar to each other. So you really need then to have a very careful analysis and characterization of the spectrum in order to identify, and then to understand better which kind of galaxy or quasar it is. So this is photometry. Spectroscopy instead is just to, like with the prism, you take your light, you split it in a rainbow, and then you can really see everything. So that's the most precise, the golden standard for characterization of any object. But what was also in principle, one would like to do spectroscopy for every object. That would be the ideal world. But unfortunately, it's much slower to take spectra. You need to find the object, decide the target, go there, takes time, take the spectra, that's it. With photometry, you take a picture, you got all the objects at the same time. With one picture, say with a wide field of view of, imagine, 2 by 2 degrees, you get thousands of objects at the same time. With spectra, you need to go one by one. Now, for example, we already had the first data release, the science verification data release by DESI, the dark energy spectroscopy instrument. And they do spectra with little robots that go and move the fibers, matching the object to be much faster than humanly possible. And so this is why Euclid is so interesting, because it does photometry and at the same time spectroscopy with some kind of special spectrograph that they have there. And also by doing this jointly, you factor out systematics, right? Because you observe the same machine, the same field of view at the same time, whatever, and the universe in these two ways. And this surely will help a lot to keep systematics under control, which is in cosmology is the main concern. Statistics, you kill it by observing for a longer time. Systematics, no. Systematics, you need to understand it. Usually it's the bigger issue. So it's a 1.2 meters telescope, it's a Koch design, I think. And now it's flying. Now it's already been deployed. It's going to Lagrange 2, where James Webb is. This will take a few months, I guess. And once it's there, will be Euclid is one of the flagship satellites. So that we've been waiting for decades. Now got the James Webb, now Euclid. There will be other big experiments going online in the next years. But this is really a milestone for cosmology.
Nice. And so using these pictures then, what would be the main objectives? What are we trying to learn using these pictures?
So an experiment of the size of Euclid will have a huge legacy science. There will be a lot of fields, a lot of stuff. But the main motivations, so this is really, like with all the other experiments, there will be so many papers, all astronomers from all the most different fields will work on them. But the really key goals is to understand dark energy and dark matter. These are the two goals. And to do that, so why is it called Euclid? Euclid is the father of geometry. And so Euclid, what its aim is to map the geometry of the universe, how it expanded, how it evolved, and so from one point to map the space-time, the evolution of the space-time, but also to map the growth of structure in it. Okay, so these are the two sides. So to understand the evolution of the space-time, then you got clustering. Clustering will be done with using the spectroscopic data, because clustering. What is clustering? Clustering is like you say in a colloquial language. If you see a cluster of people, you see lots of people all together, right? So if you are on a beach, you look at the people and you see that they are clustered. Their families and their friends, and then there are voids. Between families usually there is a gap. So this will be clustering. But to do clustering, you need a precise determination of the location of the people on the beach, for example, or the galaxies in the universe. And this has to be very precise. So you need to do, or you need to have, or you need spectroscopic redshift. Or you have spectroscopic redshift, or you have exquisitely good photo-Z, but this is quite rare. So with SPEC-Z, with the spectroscopic survey, you do clustering, and this will tell you how how the structure forming, the clustering, etc. But specifically, also we'll be able to map a spatial scale in the universe. It's a spatial scale that doesn't come from directly from cluster itself. It's a scale that was imprinted during the primordial phase of the universe. When the universe was a plasma, super hot, when it was 1,000 times smaller, and you had some this plasma of baryons, photons, and these would resonate with sound waves. And these sound waves, they imprint some specific scale in the universe. And this scale can be measured by looking at the large-scale distribution of galaxies. And as it is a fixed scale, it's an imprinted scale, like a standard ruler, we call it. If you observe this at various reshifts, then you have the standard ruler at different epochs of the universe. And so from this you can know how the space-time evolved. So you can then understand the evolution globally of the space-time. And this will be really important to, for example, understand the dark energy, its equational state, and together with the clustering of the structure, also will put strong constraints on the effect of dark energy and perturbation. So this is on one side. On the photometric side, instead, the main observable will be weak lensing. So weak lensing is lensing. So it's the fact that objects are perturbed by inhomogeneities because they deform the space-time. So if you deform the space, light rays are going through, or particles. So any object is affected by this. And so you got this. You observe galaxies far away. You have objects in the line of sight, and so the light will bend and twist and have a different path, contrary to a universe that would be perfectly homogeneous. And why it's called weak lensing? Because this is a lensing effect that does not produce, for example, double images, arches. Does not produce strong deformation. If you look at a glass of water, you will see, which you cannot see because my background. At some point, if you look at some light source, you see that caustics form very strong deformations of the light. So this is called what we call strong lensing. Weak lensing is something that is almost not visible, right? It's a very small effect that you cannot really see if you look at just one source. It's like looking through a window. A window is never perfect. As a glass that has perturbations. If you look through a window, there is weak lensing, in some sense. It's not gravitational, it's optic, like weak optical lensing, but you cannot really see it because you just see one object, and how can you know if there was like a 0.5 millimeter change in the relative position? But if you observe billions of galaxies, as Euclid will, you can combine all these observations, and then you can see the statistical effect. And we compare this, what you see, the distortion of the galaxies, of the background galaxy, because of the intervening matter structures. You can compare this signal with the expectation from your model. Now you got a model that predicts this amount of this effect, and then you compare it, and then in this way you can put very strong constraints on how much matter, how much objects there are in the universe. This is particularly interesting because 95% of the universe is dark. Right? Of this 95%, 25% is dark matter. And dark matter, so it's there is there's a lot of dark matter, right? And 10 times more dark matter in big halos, 5 to 10 times. What will gonna give you this lens effect is all this dark matter that is clustered. So by looking at weak lensing, you can directly constrain this dark matter, which we don't really understand. So it will be a direct probe of dark matter. And this is super interesting because if you look at other observables, dark matter is dark. But for gravity, it doesn't matter. Everything interacts with gravity. So there will be no, we call it a bias. A weak lensing measurement is unbiased when looking at dark matter. So this will be really, really super important to understand the property of dark matter, properties of dark energy, because both the property of dark matter and dark energy change how you form objects, how you form galaxies, filaments, a cosmic web. And yes, so these are the two main, the key observables of Euclid. But of course, there will be many, many other applications.
So we have a quote here from the physicist Lev Landau that cosmologists are often in error, but never in doubt.
Yeah.
So I don't know, could you give maybe your thoughts on this statement in the context of present day precision cosmology?
Yeah, so this is I think this is really boils down to systematics. And if you want to say the distinction between precision cosmology and accurate cosmology. So we are entered. So back in the day, I think 20 years ago, more than, no, it's right, 23, right? 30 years ago, whatever, there was really little data. So you have really little data, and so everything was quite qualitative. Your understanding, you would just see if qualitatively everything makes sense, if you got this or that. But since the big surveys, we got the WMAP, we got the SDSS with BOSS, now there's Euclid. We really transitioned to a big data. We entered the big data science class. And once you have big data, statistics go down, so you start doing precision cosmology because you have very low statistical error. But then not necessarily means that you're doing accurate cosmology, because systematics, again, are really tough. So when you say that the cosmologists are often in error because they're never in doubt, because it's so difficult to deal with systematics that sometimes then you have just to assume that you control them. So you forget that part of the doubt, right? So you can be you can be sure that you accounted for all systematics. So then you may present results that are completely wrong, that are often in error. So the classic example that they even wrote a book on it. I don't want to take on people, but the famous bicep episode, right? So they presented the discovery of primordial gravitational waves, and then was soon realized that was just systematics caused by dust. And so this is, again, they were not in doubt, right? Because they did not think about one more systematic. It was so difficult to consider all them. It's not that it's so difficult. You need to be imaginative, because systematics is not, there's not a list. No, data does not come with a list of systematics. You have to think hard and find them all. And then there is a confirmation bias, expectation bias. So you start looking for systematics at some point, and you shouldn't. And then this is why a way to fix perhaps this Landau quote is to do really blind analysis. And cosmologists started doing this really seriously. I think DES started to do super well blind analysis. So a blind analysis, what is it? Analysis where you do not the result, not even the partial intermediate result, till the very final end, of the first run. And this is really difficult because you got people, PhD students, postdocs that spent years on this stuff, and this guy, just by looking at spectra, they already tell you what is the cosmology. So the way to do the DS did it. They changed the data in a controlled way. They changed the data themselves to blind analysis. Then, of course, they put there some random mask on the parameters. So that was really impossible to know. And then they start thinking, okay, let's do all possible systematics in a kind of an unbiased way. And then at the very end, you unblind analysis. And of course, you may find issues. You may find that there are inconsistencies and internal checks that don't work. Then you already unblinded it. Then you continue and looking for systematics and fixing analysis, but then it's already unblinded. But still, the initial blinded phase is super important, yes, this is people are trying to fix this issue of systematics. Mm-hmm.
Yeah, maybe we can continue with looking at the measurements of Euclid a little more in detail. You already pointed out baryonic acoustic oscillations. Of course, I think we already measured this from cosmic microwave background itself. Maybe by measuring the same using the galaxy data, I think it would be a very nice tool to have two measurements of the same thing. Continuing with that, the nature of dark energy has to do with the growth of structures, as you pointed out. Can you maybe, to start with, can you maybe explain redshift space distortion? Maybe you subtly put that we need very precise spectroscopic measurements. Maybe you can briefly explain what is redshift space distortion.
Yeah. So earlier was mentioned this specific scale that was imprinted by the CMB, and exactly it's technically it's called baryonic acoustic oscillation. And so the big novelty here of Euclid is that we already measured baryonic acoustic oscillations in galaxies, but at very, with some error bar and at very specific redshifts, because we had the BOSS and eBOSS, WIGO-Z and other surveys, but Euclid we completely changed the level of quality of BO measurements that we were able to do, especially reaching very, very high redshifts. So we'll provide this measurement, so this specific scale from redshift 0.7 till redshift 2, 1.8, I don't recall exactly. So really we'll be able to map in a uniform, super precise way all the expansion history of the universe from redshift 2, which is many billion years ago, and is exactly when dark energy starts dominating, so it begins to be important for the universe expansion. So we're gonna map the universe expansion during all this specific and very interesting phase of dark energy dominating the universe. So redshift space distortions. It's a key features in the clustering, the distribution of galaxies. And so before I simplify the picture, saying that once you measure redshift, then you also know where the galaxy is. When you look at the beach, you see people that are, why do you know that? Why can you compute the clustering of people on a beach? Because you know that the average size of someone. I know that on average people is between 1 meter and 60, I don't know, to 1 meter and 80 on average. There are smaller, larger, there are kids, and there are gigantic people also. But on average, you know that. So this is a standard ruler. A person is a standard ruler, and so you know that you see someone this big that is far, right? So we use redshift to know the distance of a galaxy. However, redshift comes from the red shift of light due to the expansion of the universe. And there's also another phenomenon that gives you redshift or blue shift, which is just a velocity boost. like the example of the ambulance coming by and the pitch is higher, lower, etc. So when you measure, when you see a galaxy, you can measure to the best possible precision or virtually without error the redshift, but you still do not know the distance because this redshift is given by two sources. The redshift due to the space-time expansion of the universe, and the redshift due to the particular velocity of that galaxy that is there. So in principle, one says, damn it. So we have a limit to understanding, right? Because there is this source of noise. But as always in astronomy, for at least in cosmology, if you are able to model the noise, right, to understand the noise becomes signal. So that's the trick. So people have worked out exactly how peculiar velocities are in the universe. What is the relation to clustering on scale, and a pioneer in this was Nick Kaiser, right? He passed away just I think last week or the week before. It's a big loss for the community. So you give it the name to a Kaiser effect. But anyway, people have developed this effect at the linear, the first order, second order numerically simulations. So now we understand very well the effect of peculiar velocities on redshift, and actually this now becomes an observable itself. So you can use you have your cosmological model. You predict how much light sphere distortion you see clustering, because this affects galaxies, the velocity of galaxies only on the line of sight. Because if the galaxy has a velocity which is perpendicular to the line of sight, the effect is zero. Now in GR is proportional to a higher power of the velocity, so it's basically there is no effect. And so you can predict how the measurement should change because of peculiar velocity given by your specific model. You compare it with data, and again you have actually one handle more to constrain the model. So this from a virtual problem became one more observable to master. So this is shows the cosmology community really worked hard during many decades to reach this level of understanding of the cosmos.
So the other thing which Euclid is known for is that it is going to do this redshift survey. You also pointed out DAISY. So what exactly is a redshift survey? Because when we see the sky, it's usually the two-dimensional sheet. So what is this redshift survey, and what is it to have a 3D map of the universe?
So for clustering needs spectroscopy redshift. So just you don't do it. So that's it. With cleansing, however, right, you could also, in principle, do it without redshift information, right? You do it. You project everything on the sky. So you look at all the galaxies, everything projected, and that's still unobservable. So if there's nothing else that you have, then you work with that, and then you compare your projected predictions to that. But then people starting, trying to do better, and then, for example, Euclid has a photometric redshift, which it's similar to spectroscopic redshift in the sense that you still constrain with this measurement the distance of a galaxy from you, but it's based just on a few filters, and it has a much larger error, much less. So a good spectroscopic redshift is virtually without error, almost. It's almost insignificant. Photometric error can be depends exactly. For Euclid, honestly, I don't remember, but might be 1%, 2%, 3%, and I don't recall exactly the figure. And also there is a fraction of so-called catastrophic outliers. They are simply object that get a redshift is completely wrong, and they just pollute the data set. Okay, anyway, we have statistical tools to take this into account, etc. So what you do once you do picture of the skies, but all these galaxies, even if you have automatic redshift, which is not so precise, still you do what we call tomographic lensing. So you start looking at the effect of lensing on galaxies by not looking at everything projected, by divided in shells of distance from the observer. And this is really important because you can imagine, of course, that how much more information do you have if you look at the universe divided into, say, 10 shells in Redshift, in comparison to projecting everything together, like in a sandwich. So you can, this really improves a lot, and this is something that has been, Euclid is not the first, of course, to do this. We have kids, another survey that, for example, DS, we have also that present the results. So these are two recent surveys that did tomographic lensing. And so this, I guess this is the possible answer, right?
Yeah. So one last question about lensing, which is another milestone which Euclid is doing. So as you mentioned, everything is bent around when you consider Einsteinian gravity, then light rays bend when there is matter, and matter and light experiences kind of same kind of curvature. But when it comes to modified gravity, light and matter doesn't obey the same kind of potentials or same kind of curvature. So this would be kind of a new parameter which we can test using lensing. So can you maybe point out, like, can we use Euclid to make some precise measurements of these parameters?
Yes. This is a very good. You went precisely to the technical one of the technical key goals of Euclid, and indeed, so although Euclid, what Euclid officially promises is to constrain super well the standard model. So you also need to remember that the standard model with cosmological constants and dark matter is the baseline way to treat data, analyze them, and also the baseline model that is used to calibrate everything. Having said that, so the Euclid first goal will be to constrain that and to possibly rule it out. Right? Then, of course, you want to test extended theory, alternative models to the standard model. So with different dark matters and different dark energy. So dark energy, you can have two sources of kinds of dark energy. You can have what we call a time-dependent, a dynamical cosmological constant, so that kind of a vacuum energy, that is not constant. So this, for example, is given by a scalar field, the same scalar field that would give you inflation during the primordial phases of the universe, can also give you a behavior which is very similar to dark energy. But this is, again, this will just it's different, it's qualitatively different, but not so much, because a scalar field, for example, has a regime that becomes very similar to vacuum dark energy. Now, if you instead have a modification of gravity, so you can always play this game in astronomy. You can either introduce a new source, dark energy, dark matter, or you can modify your theories. In the theories we have, baryons, you cannot really modify baryons too much, because the standard model is the most verified, tested model that we have. And you have really little room to change. Of course, you can introduce coupling to exotic particles, but be careful, because this, you could have observed those at LHC, at other experiments. So there is not easy to change the standard model particles, but you're totally free to do whatever you do with dark energy and dark matter. Right? So on one side, you can add these two components because being dark, you're really free. You just have to fit the observations, the dynamics, the effect on lensing. On the other side, you can change your theory. So you cannot change standard model of particle physics. So you can change your standard model of gravitation, which is general relativity. You can do that to replace dark matter, and then you go to these Mondian theories where you change the strength of the gravity interaction for a given scales of acceleration, right? To explain rotation curves. This is interesting possibility, but doesn't really seem to work. And the other alternative is to change gravity to explain dark energy. And this is what we call, like an umbrella term, is modified gravity. Right? So a prediction of modified gravity is that you can have so-called anisotropic stress, that is the difference between the two potentials that otherwise in relativity are very similar to each other. And this is really a smoking gun. If we manage to measure this with lensing, then this is Nobel Prize. Like immediately go to the stock to get it. So this is really will be revolutionary. Will change everything. Of course, everybody's hoping to see something of the kind. Yeah.
Yes.
And so talking there about constraining different things in cosmology, how much better is Euclid able to constrain these things compared to some of its predecessors?
Enormously, because so DS and kids, they're incredible surveys, but they're from Earth. And Euclid, being outside, can capture all the nice infrared emission. And indeed, it's very sensitive infrared light, which is the atmosphere is opaque to it mostly. So that's why it can measure basically all galaxies up to Redshift 2. I mean, this is simply out of reach for the other surveys. So will be really a game changer. The figure. So there are some quantitative measurement of improvement, but these are. One people use them mostly to convince politicians because it's a little bit too simplistic to summarize the impact of Euclid. So the way people do this is to forecast constraints on the equation of state of dark energy. So you parameterize it in this Taylor expanded way with W present day W naught present day equation of state at a given time. So you just do a parameterization, which is anyway a non-logical one, no much insight. That's not necessarily the optimal one. And then you constrain in a plane with W naught to WA. You forecast from weak lensing clustering the constraints on these two parameters will give you some little area, an ellipse. Then you measure the area. Then you do 1 over that area, and that will give you what people call the figure of merit. And people use this to compare different experiments. So it's very simplistic and again, it's used to get funds and build telescopes. But I think we will understand the impact of Euclid only when we start having the data, because these analyses are anyway based on they don't include systematics often, are very simplistic, and things can go a little worse, or even better, right? So, and of course, we're done many years ago. So, quantity will be a game changer. So, how many times better constraints is, I think, is I'm not sure. But it also, because the thing is that it is able to detect modified gravity, dark energy, weird dark matter, and these are like threshold effects. Not really interesting to know how many. Just that it's sensitive enough to be able to do that, even if this is 3 times, 10 times doesn't matter, right? It's available to. So sometimes people put it in this way, Euclid. So if Euclid, by the end of its 5-6 year mission, confirms the standard model, then that's it. This is conclusive evidence that the universe is described by the standard model. If it doesn't matter if dark energy, dark matter are dark energy is cosmological constant, dark matter is a weakly interacting massive particle, doesn't matter. That kind of description is the correct one. And then you can interpret it fundamentally the way you want. That will be conclusive evidence because it is such a deep survey with so many, basically all the observable universe, because you can observe a third of the sky. Now my Milky Way takes half of it anyway. So there's Euclid 2 can improve so much. So of course there will be future better surveys than Euclid, but won't perhaps be able to if Euclid finds that trans-CDM is correct, it won't be able perhaps to exclude lambda CDM. I mean, this is so we'll see. We'll see, but something we'll understand. A lot we'll understand. Yeah.
Nice. And I think, Joel, just to go back a bit as well to where you're talking about the standard model and how this is such a well-tested theory. So, I mean, for particle physics, a lot of our experiments we can do here on Earth, where we can have contact with the experiment, and really have much more control over it. Whereas we'll say with cosmology, we're looking out to space and we can't go there to control the experiment or have any contact with that. We really have to derive our theories from whatever it is we see there and try to draw on the information we can get. Could you maybe elaborate a bit on the difficulties associated with having to deduce our theories from the experiment like this?
Yeah. So this from one side, this goes back to the systematic issue that we already discussed. From the other side, comes also from the that we need to simplify assumptions. I think cosmology. So, of course, in every science you do simplify assumptions, but these are a kind of less important, perhaps, and less also philosophical sometimes. So a common assumption that without it is difficult to do cosmology, even though people, including myself, are trying to do, is, for example, changing the background cosmological model that we assume. The background space-time metric, actually, not cosmological model. So because exactly for the reason that you said, that we cannot go there and see, right? We cannot take a jump of a couple of billion light years and check out the universe. We have to suppose that the universe is the same there as here. Of course, we believe in the laws of nature are universal. There are many levels at which something can be universal. So there have been people working on variation of fundamental constant. There'll be some measurements some 20 years ago, claims of a change in alpha, then this claim disappeared. But nevertheless, from a at least a philosophical conceptual point of view, and the way you interpret data is that when we do standard cosmology, you assume that all the laws that we have are the same at all time, at all distances. Now, the model can be still universal and be therefore a good model that can predict things, but still their constant could change. You just have to couple scalar field to the electromagnetic tensor, you have a change of the finite structural constant. And this is totally fine. It's a model and it's not uglier than other models. And but this will complicate everything. Will change the transition lines, will change, how do you find Redshift then if the transitions change themselves because of this changing in alpha? And equivalently, you could have, so we interpret the universe according to the fact that it is homogeneous and isotropic at large distances, at very large scales, statistically isotropic and homogeneous. And this comes from, again, from philosophy, because we want to be Copernican. We want to be the same, have the same chances of observing the same universe as an observer that is 5 billion light years from here. And this is fine, and it's agreement with observations. But again, we are assuming this. So we are assuming a bunch of stuff that lets us simplify the universe and remove this problem that we cannot get there, right? So this is something that is peculiar to cosmology because of this reason. In other fields, you don't have to assume that you're doing the experiment on your desk and that's it. Not that I do it now, I'm not doing it 5 billion years ago. Even if alpha changes, it's not gonna change in 10 hours, right? Or in 10 years. Changes are cosmological anyway. So this is a thing. I think actually I'm personally very interested in these topics because being the community is so ignorant regarding dark energy, dark matter. It's really 95%. I think is interesting. It's also necessary to test basic assumptions, and these basic assumptions are, for example, can be variational constants, the homogeneity on large scales, and others.
So maybe the last question is now it is launched. So when can we expect the Euclid data to be available to do some cosmology?
So I guess I used to be a member of the Euclid collaboration, and when I was working in Germany. Then once I moved to Brazil, I became an external collaborator because Brazil is not supporting Euclid, right? So so I couldn't be in. But I've been following, collaborating with the people there. However, because of this, I'm not super up to date with exact times. But my guess would be that you have a few months to get there to Lagrange 2. There will be at least half a year of science verification commissioning that you need to test and everything, like similar to James Webb, right? Then usually you do the first year observations, then you do a first data release. So this data release, what will mean? Will mean that there will be a bunch of papers coming out, probably from start of observe. Say that now it's July, perhaps the beginning of next year, observations really start. And then you'll have, after 1 year from that, they will have a first year of data, they will analyze it, and they will put some papers. So it will be then mid-2025, first bunch of paper. Data will not be necessarily accessible to everybody immediately, right? There will maybe some embargo time, depends on the internal rules. The rules have been negotiated with ESA because, there are all these things that people want to give the data back to the community because it's been paid by the community, but everybody. So data should be public as soon as possible, but there should be some embargo, of course, for the scientists to explore the data before someone else can. And then that will be the first data release. Then probably will be a 3-year data release, 5 or 6 years. Then there will be, once Euclid is done, there will be, of course, other data releases, people refining the data. Actually, those will be the most robust one because by the time there will be 10 years of understanding of the data and they will read clean of systematics and everything. So perhaps the first results will be, say, in 2 years from now, I would say. Like first papers, I guess, or even before, but I would say like a couple of years.
Okay, very good. So yeah, I think that's everything. It's been a very interesting talk. I think really driving home how important Euclid will be for cosmology. So thank you, Valerio, and
okay, thank you, guys.